Earlier we have seen PLLs where the output frequency happens to be the same as the input frequency. Okay. Today we will just talk about the clock multipliers where the output frequency is output frequency is sum n times of the input frequency. Okay. So, it is not only the output frequency does not need to be same as the input frequency always. So, the analogy for that you can think about from the voltage follower. So, we have seen using an amplifier, I will just help you to understand a simple voltage amplifier where you apply an input voltage V in and you get an output voltage V out. This resistor happens to be K minus 1 R and this resistor is R. If the amplifier is ideal, you can work out this circuit. If the amplifier is ideal, V out by V in is equal to K. And a simple way to work this out, if the amplifier is ideal and we know that this circuit is in negative feedback, these two terminals are going to be same. I call this as VFP, and in this case actually VFP is equal to V out by K. Okay. And this V out, VFP and V in have to be equal because it is in negative feedback. So, it is a straightforward way of calculating it. Now, what you need to draw or conclude from here is the following. To make sure that V out is K times V input, we are comparing V out by K, which is our V feedback, with V in. So, you have an amplifier whose output voltage is K times the input voltage. You are not comparing directly the amplified output voltage with respect to the input. You are dividing that output voltage, and comparing the divided output voltage with input, and the closed loop feedback is ensuring that the feedback voltage is same as V in and the feedback ratio is 1 over K. So, your output voltage will be K times V in. The same thing happens in clock multiplier. So, for example, let us say I do not know how I will get the whole circuit. I have this V in and here I have V feedback signal, right. The output of this PLL we have been doing it for a lot of time. So, let us just continue with that very simple example, this loop filter, and you have a VCO. And this is V out. What I want is the following. I want V in as sine of omega t and I want V out as cosine of n times omega t. This is what I want. I want the output frequency to be n times the input frequency. If I connect it like this, the way we have been connecting it, right. We have seen if you connect it like this, the loop is going to force your output frequency to be equal to input frequency, because that is what the loop will do. If it does not do that, then the phase error will keep on always changing, you will never reach any steady state. So, that is not going to happen here. If we want the output frequency to be equal to the input frequency, we cannot make this connection. If we cannot make this connection, then what do we need to do? What we need to do is, we need to find a block somehow, which we do not know right now how, somehow that the feedback signal has the frequency equal to the input frequency. The VFB signal, if we want to lock this and reach any steady state for this block, VFP should have same frequency as V in. Well, if that is the case, it means I have to divide the frequency. Okay. So, what I need to do is, if I have omega out here, somehow I need to get omega out by n here, right. If I get omega out by n, okay, if I get omega out by n at feedback signal, then I will compare omega out by n with omega in, and loop will enforce, this is a negative feedback loop, will enforce omega out by n as equal to omega in. Okay. Keep this difference in mind between a voltage follower and a PLL. In case of voltage follower, you were dividing the voltage. So, if I happen to do this, I know V out is cosine omega t, I just divide the voltage using a resistive divider the way I have been doing for voltage follower. What will I get? V feedback as 1 by n times cosine of n omega t. Does it divide the frequency? Not at all. Okay. It does not divide the frequency at all. So, you cannot use this kind of resistive network here, it is not possible. Okay. So, what you need to do is, how we do it, well, that is for the course that you will come to know about it, but what you need to do is, you need to somehow divide the frequency. Ideally, VFP, you can have any gains in the signal, maybe let us say A1 times cosine of omega out by n times t. This is what you want. Okay. So, just to make sure that you follow this, if my output signal happens to be signal like this, okay, and I want to divide the frequency by 2, I want a signal like this. Okay, how you are going to do it, that is something which we will see later. So, you need a block called frequency divider. Okay. You need a block called frequency divider. If you do that, then you can enforce in this case. Okay. So, if I have the frequency divider here, I will in closed loop, the loop is going to be locked only when locking condition for clock multiplier. This is also a phase lock loop, by the way. Okay, do not think that this clock multiplier is different from phase lock loop, it just has a frequency divider in the feedback path. It will have omega out equal to n times omega in if this frequency division ratio is n. Okay, you should be able to choose different n. One condition is this, and this condition always remains d phase error by dt is equal to 0. Okay, and this d phase error by dt, what is the phase error? Well, phase error at any given time is your omega in times t minus your omega feedback times dt. I will write this in integral because omega feedback can change. So, this is your phase error. Okay. So, you should be able to lock the PLL, okay, with a frequency multiplication at the output, right. If you look at it, this is little interesting that omega in t, integral t is phi in, okay, 1 n is a constant here, I can take n out do this omega out integral dt. What is omega out integral dt? That is phi out. Okay. So, what is interesting here? If you are dividing the frequency by n in the feedback path as shown, then for the phase you are actually dividing the output phase by n. Your feedback phase is output phase divided by n. So, a small signal model of this PLL will be your phase error detector like this between the feedback signal, okay, with gain KPD, loop filter transfer function, whatever loop filter you would like to use, you can use, okay, and then your VCO with gain K VCO by S, and K VCO by S is going to give you the output phase, and because you are using a frequency divider, your feedback phase gets divided. So, this is divided by gain of 1 over n, and this is feedback phase, this is input phase. Okay. Here your feedback phase is equal to output phase by n. The loop gain for this particular loop is equal to KPD times loop filter of S, K VCO by S. You have now 1 over n in the feedback path. So, loop gain will have this transfer function. Okay. So, we will implement clock multiplier in this course, and we will go into detail of each block from the next session. Okay. Thank you.